Welcome back, everyone. Today, we're diving into something truly fascinating. We are going on an exploration into the hidden microscopic structures that literally shape the physical world around us. In this explainer, we are looking at the invisible architecture of chemistry. We're going to decode a concept that might sound a little intimidating at first, but is actually the secret code behind how our universe builds such incredible diversity out of a very limited set of building blocks.
Okay, let's dive into this with a paradox that absolutely blew my mind when I first saw it in our source material. Seriously, how is it possible that drinking alcohol, the stuff in your standard beverage, and an anesthetic gas, the heavy-duty stuff doctors use to knock you out before surgery, how can they be the exact same thing? Well, to wrap our heads around that, we really have to look at the raw ingredients. Both ethanol, your drinking alcohol, and dimethyl ether, your anesthetic gas, share the exact same molecular formula. It's C2H6O. That's 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom for both of them. It's kind of like having the exact same pile of Lego bricks, right? If you snap them together one way, you get a refreshing drink, but snap them together a slightly different way, and boom, you've got a gas that puts you right to sleep. It's literally all about the architecture.
So, to unpack all of this, here's our roadmap for this explainer. First, we'll look at the isomerism mystery. Then, structural isomers explained. After that, stereoisomers in 3D space. And finally, why isomerism matters. Let's get right to it.
Part 1, the isomerism mystery.
Let's kick things off by defining the actual science behind that wild paradox we just talked about. Isomerism is the existence of 2 or more compounds that have the exact same molecular formula but completely different arrangements of those atoms, different spatial orientations, and because of that, entirely different physical or chemical properties. In chemistry, knowing what atoms you have in your bucket, that's really only half the story. How you arrange those atoms is what actually dictates reality. And compounds that do this, we call them isomers.
Moving on to Part 2, structural isomers explained.
Now, what's really interesting about this is how the actual flat two-dimensional connections between atoms change. Our source material gives us some incredibly handy memory tricks to keep these structural isomers straight. So when the carbon chain arrangement changes, it's chain isomerism. Just remember, chain changes. Simple, right? When the position of a functional group shifts, that's position isomerism, or position changes. And when the entire functional group is totally different, like our alcohol and gas example from earlier, that's functional isomerism, meaning function changes.
Let's actually see that chain changes rule in action with the formula C4H10. You can build N-butane, which is just a straight unbranched chain of carbons, or you can build isobutane, which has a branched chain. And the source points out something wild here. Just by branching the chain, the molecule actually gets a lower boiling point. Same exact atoms, lower boiling point, literally just because it's branched. How cool is that?
Next up is our position changes trick. Check out 1-butene versus 2-butene. The carbon skeleton here is identical. The only thing happening is that the double bond is basically packing its bags and shifting its position over by just one spot. That simple little relocation, it means these are entirely different position isomers. All right, let's move to part 3 and see how this builds stereoisomers in 3D space.
Up until now, we've really just been looking at flat, 2D connections on a page. But, of course, molecules exist in 3 dimensions. And to understand 3D stereoisomerism, we first need to meet the chiral carbon. A chiral carbon is an asymmetric carbon atom attached to 4 completely different groups. In chemical diagrams, you're going to see it marked by a little asterisk. It is basically the absolute anchor point for optical isomerism.
And because of that chiral carbon, molecules can form these things called enantiomers. The source material uses a really fantastic, relatable metaphor here, like a left hand and a right hand. So if you hold your hands out right now in front of you, they are perfect mirror images of each other, right? But try laying your left hand perfectly flat on top of your right hand, palms facing the same way. Your thumbs stick out on opposite sides. No matter what you do, they cannot be superimposed. Well, molecules do this too. They can be exact mirror images, but geometrically impossible to perfectly overlap.
We also have another type of 3D arrangement called geometrical isomerism, and this happens because of restricted rotation around a double bond. Just look at how the properties behave when we compare the cis and trans forms. In the cis form, the same groups are on the same side of the double bond, but in the trans form, they're sitting on opposite sides, and the properties completely flip. Cis has more polarity, a higher boiling point, but is actually less stable. Trans, on the other hand, has less polarity, a lower boiling point, but is more stable. All of this just depends on which side of a double bond the groups are sitting on.
So, if you're ever looking at 2 compounds and trying to decode their relationship, the text gives us this flawless, really elegant 3-step procedure. Step 1. check the molecular formula. Are the ingredients exactly the same? If yes, keep going. Step 2, check the connectivity. Are they wired together differently? If they are, boom, it's structural isomerism. Step 3, if they're actually wired the exact same way, then check the spatial arrangement. Do they differ in 3D space? If yes, you are dealing with stereoisomerism. It's just a super logical checklist.
Which brings us to part 4, why isomerism matters. We've been zoomed way in on an incredibly microscopic level today, looking at bonds and 3D rotations. So the crucial point is, why does this actually matter to us out here in the macro world? Well, because this invisible architecture governs literally everything. In the food industry, different isomers are the reasons something smells like a fresh lemon instead of an orange. In our biological systems, the very structure of our DNA and our proteins relies entirely on specific stereochemistry. But honestly, the highest stakes are in pharmaceuticals. The source points out that with some drugs, one optical isomer, let's say the right-handed version of the molecule, will successfully cure a disease. But its exact mirror image, the left-handed version, it isn't just ineffective, it can actually be highly toxic. The only difference is the 3D twist of the atoms. Mind-blowing, right?
And that leaves us with a pretty profound thought to end on today. If a mere microscopic twist in a molecule can literally change a cure into a poison, what other invisible architectures are silently shaping our world behind the scenes? Chemistry really isn't just about what things are made of. It's about the geometry of how they're built. Keep that in mind next time you look at, well, anything around you. Thanks for joining me on this explainer, and I'll catch you on the next one.